This meeting is being recorded.
The next section in Chapter 4, 4.7, is a discussion on conformational analysis. So we looked at Newman projections for the first time in section 4.6, and now we know that there are different conformations due to that free bond rotation in our carbon-carbon single bonds. So that's what we're going to explore a little further here. So between, so say this is ethane, right? We have our front carbon here with 3 hydrogens, and then our back carbon with the same. So we see here the angle between the 2 hydrogens that are coming off of our front and back carbon. This is a dihedral angle. That's the term that we use. And it's about 60 degrees, right? Or it's exactly 60 degrees because we know a full circle is 360 degrees, and divide 1/6 of that. That's where we end up with that 60-degree dihedral, or also it's called a torsional angle. When we talk about torsional strain, it will make sense why we call it this. So we have different conformations. So this lower energy conformation that we'll pick out here, we'll just look at 2 different conformations to start. The lowest energy conformation is called the staggered conformation, where the hydrogens are all spread out, right, from one another as far as they can be, versus the eclipsed structure where the hydrogens are kind of blocking one another. This would be a higher energy conformation. To exist in this state, this molecule needs more energy because these electron clouds of these hydrogens would have repulsive forces, right? So they would be repelling each other, these groups, and we would need more energy to keep this conformation. So this is our highest energy conformation over here on the right. The lowest energy conformation, it doesn't have those repulsive forces, and we don't have that torsional strain when those groups are eclipsing, right? So that's why we have this lower energy, and we attribute it to what we call torsional strain. And the energy between these 2 conformers, these 2 conformations, is about 12 kilojoules per mole. So let's look at that graphically really quick. So we have our lowest energy conformation here, and then these are all degenerate, right? These structures here, as are these low energy conformations. So we have one versus the other. We have all the staggereds down here, staggered conformations, and then we have our eclipsed conformations up here. And they're all degenerate, equal energy, but we see that our energy difference between one versus the other is about 12 kilojoules per mole. So the lower energy conformation, that's the form that you're going to see your molecule experimentally more in that phase because it's lower energy. So it's going to appear in that phase more commonly. So say we look at ethane again here, and the rationale behind these energetics, right? Why we see these different energy values for the eclipsed versus our staggered conformation. So as I mentioned before, the electron pair repulsion between the eclipsing bonds are what are going to cause these repulsive forces, right? These difference in energy. So when we have the eclipsed form, what we see is 3 hydrogens that are overlapping, 3 groups of 2 hydrogens that are overlapping. The total energy difference, the total cost, they say here, to get to that form will be about 12 kilojoules per mole. So we can attribute, dividing by 3, each of these hydrogen interactions to be about 4 kilojoules per mole. So again, at room temperature, about 99% of whatever quantity of molecules you have will be in the staggered conformation, and then about 1% would have enough energy to be in the eclipsed form. So there's not really a fully accepted, I guess, explanation for this, but they believe that this is due to the stabilizing interactions. If we go back to molecular orbital theory, if we have our bonding orbital here, our sigma bonding orbital versus our sigma star over here, our anti-bonding orbital, they don't know this for sure, but they believe that somehow an overlap between a bonding sigma and a sigma star molecular orbital are what create this stabilization effect with the staggered conformation. Right, we have this side-to-side overlap with an empty molecular orbital. And that's what we see down below as well. Something similar. This is the bonding, and then this will be the anti-bonding on the right, or on the left. So you won't need to know the details of that, but this is much more important if we look at propane. And again, we'll look at the torsional strain for propane. So that will be this value here that's shown to go from our staggered conformations. Notice the only difference is that one of the hydrogens has been replaced with a methyl group now, because we have 3 carbons in our chain. So we're only looking at the 2 carbons in the Newman projection. So the third is given as in place of one of the hydrogens. So we have our staggered down here. And again, these are going to be our lower energy, right? Our lower potential energy. So most of our molecules will be in one of these forms versus our eclipsed. And we see that the difference, the torsional strain, is about 14 kilojoules per mole between the staggered and then our eclipsed up top. So this barrier to rotation is another way of describing that energy. And this 14 kilojoules per mole is about 2 kilojoules per mole than what we see for ethane. So our 2 carbon chain versus our 3 carbon chain. Why so? Well, we've already looked at how both of these effects of the eclipsed hydrogens are attributed about a 4 kilojoule per mole energy difference when we divided 12 by 3. So the difference here would be about 6 kilojoules per mole, this energy cost to eclipse a hydrogen with a methyl group. So that's what they attribute this difference in value to. Now we have a methyl group, so it's a little more energy to get it to stay in that form. So we will continue with some conformational analyses in section 4.8 in the next video.